In this video, I will talk about the concept of reachability and controllability for both continuous and discrete time dynamic systems. Okay, so the reachability and controllability are the concepts that are only related with the state evolution or state update equation. Ax plus bu. We technically don't need to write the output equation from this perspective. Okay, so in order to talk about the reachability of a system, we need to talk about the reachability of a state or controllability, of course. We say that xd is a state is reachable. Okay, so it's a definition if there exists a time interval. It's a finite interval. Okay, 0 tf. Okay, tf, this is t, and associated control input, which is defined in this interval. Okay, such that x of t is equal to xd, where x of 0 is equal to 0. Okay, so if we parse this statement, technically x of t is called reachable if we can find an input pair on a finite interval such that at t is equal to tf, x of t will be equal to that state. So technically starting from 0 and we are trying to reach a state. Okay, so in reachability, we don't need to stay at that state like for some time interval. So it can be an instantaneous time, but if we can reach it, then it's a reachable state. So starting from 0 and going to a state, and if we can find an input and time pair, of course, associated with the time dynamics, this state is called reachable. Okay, xd is called controllable. Okay, so it's dual. So if there exists a time interval, it's the same thing. Okay, 0 tf, it should be a finite, and we need to find an associated input vector which is defined on the interval such that when x0 is equal to xd, so we are starting with a non-finite or non-zero initial condition, and x of t is equal to xd. So in the controlled idea, we start from an initial condition. Okay, it's a non-zero initial condition, and if we can, okay, this is wrong. So this is better. If we can reach the origin in finite time with a, of course, available control input, we call the state as controllable. So here the point is, u of t should be defined in a finite time frame, and it should reach the 0 in finite time. Okay, so for example, it's possible that we may not have an input, okay, but the system is stable. We know that the states will go to 0 if the system is stable, but it will be asymptotic convergence, and we can reach the 0 exactly only at time is going to infinity. Okay, here the idea is starting from an initial condition, going to 0 in finite time. So x of t is a reachable state, x of f, let's say x of r, or let's say that, is a reachable, and x of t is a controllable state. So how we can talk about the reachability of a system? So it is simple. First of all, we need to talk about vector spaces. Okay, the set R, it's a set of all reachable axes. Okay, so set of all reachable states forms a vector space, a linear subspace. Okay, let's call it like this, and it is a subset of Rn. So the idea is it's a linear subspace. Okay, if you don't remember what's a subspace or what's a space vector space is, I really recommend you to go and read your linear algebra lecture notes. Okay, so technically we have a set. It's subspace, and this set is composed of all possible states that we can reach from 0 to that state. Okay, that's simple. Similarly, set of all, let's like this, of all controllable states forms another linear subspace. Okay, so it's like this, and it's also a subset of Rn. Okay, so technically all of the sets, the initial conditions, where we can find an input that can technically derive this initial condition. 0 is forms a vector space, and this set is technically a subset of, or technically a subspace of Rn. Rn is technically, and we know that X is an element of Rn. That's great, right? Okay, so what is the relation or what is the difference between reachability and controllability? Let's, okay, have a clean page. That's great. Okay. For continuous system, the good thing is if X is an element of reachable subspace, it is also an element of controllable subspace. Okay, let's like this. And it's an if and only if statement. So if a state is reachable, it's also controllable. So for continuous time dynamical systems, reachability implies controllability. And we don't need to talk about two different definitions. Okay, so for this reason, if you look at different textbooks, some people use the term reachability, some people use controllability. Sometimes you will see that even the definitions are different. For example, you can see that a state is reachable, okay, if from an arbitrary initial condition we can go to that state, it's reachable. Or from an arbitrary initial condition, if we can reach that state, it's controllable. So it's kind of, you can even see that even the definition are mixed if you are talking about continuous time dynamical systems, because there is no ambiguity. Reachability, controllability are equivalent definitions, and both like mathematics and everything is same. Okay, that's great. So, okay, so when we call a system reachable, very simple. If R, okay, which is this, this is bad, okay. If R, which is where R, it's a subspace which composed of all of the reachable subspace, is technically equal to Rn. So very simple. If reachable set is the whole subspace that the state space lives, then of course the state space representation is fully reachable. If R is a subspace of Rn, but R is not equal to Rn, then the system is not fully reachable. There could be states, vector spaces that we can reach, but it's not fully reachable. And from the perspective of control theory, of course, we want our systems to be fully reachable for many practical and theoretical reasons. Okay, so it's the same thing. So if it is fully reachable, it's fully controllable. Okay, so keep in mind, reachability and controllability are equivalent in terms of the imposed mathematics, details like subspaces. Reachable subspace is equal to controllable subspace. If the system is fully reachable, it's also fully controllable. So in the continuous time systems, we may use like reachability, controllability, just replacing even in the same paragraph, okay, because they're technically equivalent. So how we can check a system is reachable or not? If you remember from your feedback systems course, we have a controllability or reachability matrix where we form it like this: B, A, B, A square B, and it goes like this until a to power n minus 1b. So of course I can change the order, it doesn't matter. So it can start with b or go to n to power minus 1b, or it can start with a to power n minus b to go to b. So this is a controlled reachability matrix, and it's very fundamental from this concept, because if rank of m is equal to n, or similarly if range space of M is equal to Rn, the system is fully reachable. Okay, so what is rank? You should remember from your linear algebra courses, but let me remind you. So if this is a square matrix, okay, so for example, m by n, 4 by 4, 5 by 5, this is technically equivalent to looking at the determinant of m. If determinant of m is not equal to 0, it's a non-singular matrix, rank is equal to n, it's fully reachable. You can comment on it. But if this is a multi-input system, for example, we have two inputs, we have for example 10 states, or it doesn't matter, this won't be a square matrix, it will be a fat matrix. Okay, so what is rank? Rank is technically the number of linearly independent columns. Okay, so if it's a for example fourth dimensional system, its dimension is fourth order. Okay, so if you have two inputs, your m will be like, I don't know, element, let's say your m matrix will be element of R, let's say it's 4 times 8, so it will have 4 rows but 8 columns. But if you can find 4 linearly independent columns, then rank is equal to n. And what is the range space? Range space is the space that can be spanned by selecting each of the column of the n. Technically, being rank is equal to n, which is the dimension of the technical state space, is equal to range space being equal to Rn. Okay, so these concepts are important, especially from the perspective of true-false questions. It's nice to understand the mathematics behind this kind of techniques, because in control theory, you cannot avoid mathematics. It's important. And I think if you know linear algebra better, you will understand these topics better. Okay, that's good. So we know that. I think there is nothing new from this perspective. Okay, now let's talk about reachability for discrete time systems. Okay, that's great. So we have a discrete time equation like this. Xk plus 1 is equal to a, let's say, you can say ax times k plus b times uk. Again, we don't need to use the output equation, because reachability is all about reaching and controlling state. So, well, what is reachability? We have a slightly different definition. X of d is reachable, okay, if there exists a u of k, okay, so input signal, such that, okay, so x of, let's say, kf and is equal to x of d, given that x of 0 is equal to 0. Okay, it's very similar, right? So as x of d is reachable if you have an input vector which can drive the system from 0 to x of d in finite time. Okay, so it is very similar. Okay, and the idea, the main difference from the reachability and continuous system is this kf can be finite, but for example, it may be equal to 10, but you may not reach it in 9 steps, for example. It's also possible. But in continuous time systems, if you can reach a state in technically t is equal to 10 seconds, you can reach that state, so anytime that is not equal to 0. Okay, so here, this is the main idea. If you can reach this state with an, of course, appropriate input vector in finite time, then the state is reachable. So x of t is similar. X of like controllability. X of c is called controllable. If there exists another input vector, it can be similar or it can be different, such that xkf, so, and it should also, there should be exist some kf, is equal to 0, given that x of 0 is equal to xfc. It's very similar, right? So if we start from an initial condition, and if our state will go to 0 in finite time for an of course available appropriate input vector, we call it controllable. So from this perspective, you can clearly say that the definitions are very, very similar compared to the continuous time case, and it should be similar. In state space generally, we talk about very similar concepts. Okay, very good. And similarly, set of all reachable states forms a vector space, and it's a subset or subspace of Rn. Similarly, set of all controllable states is a subspace of Rn. So the question is, in continuous time systems, we know that this R is equal to C. So set of all reachable states are equal to set of all controllable states. Okay, so here's the problem. This is not equal in general. It may be equal for some systems. It may not be equal for some systems. So technically, one of them cannot directly imply the other. Under some conditions, we can do that, but it is not a general concept. Okay, good. Again, we talk about this. So what's fully reachable state space representation? It's the same thing. If R is equal to Rn, the system is fully reachable, because set of all reachable states is equal to Rn, the space that we live, it's fully reachable. And similarly, if C is equal to Rn, it's a fully controllable system. So definitions are technically very similar. I will talk about how we can compute or how we can find if a system fully reachable or not in a couple of slides. But now I want to show you an example, and this example is very illustrative and important, where reachable subspace is not equal to controller subspace. Okay, so let's change it. So this is my system. Okay, 0, 1, 0, 0. Okay, it's one of my favorite systems for this course. Okay, and it is 0, 0, u of k. So it's kind of weird system, right? It's an autonomous system. So what's an autonomous system? From the perspective of control theory, if there is no input. Okay, so there's input, but e is equal to 0. So if the system is reachable, of course, it's not reachable because when x0 is equal to 0, if there is no input, x of k is equal to 0 for all k that is greater than or equal to 0. So because we cannot draw the system with any input, so it is not reachable. Okay, that's good. So what about controllability? So what is controllability? We start with an arbitrary initial condition, right? Okay, and x naught is arbitrary, and we want to test if x naught is controllable or not. We don't have any input, but we have a system. So what is x of k? X of k is equal to, this is, let's say, called g times x0. Okay, so what is x of 2? No, x of 1, sorry for that. X of 1. So if you remember, x of 2 is equal to g squared times x0. Okay, good. So let's look at the matrix. If you take the square, you will see that this is equal to 0, 0, 0, 0 times x0. And this is equal to 0 state, no matter what you do. Any initial condition will go to 0. Why? Because the system, the open loop system, uncontrolled system, or let's no input autonomous system is already in that bit condition, which will reject all of the initial conditions in finite time. Because so from the perspective of like transfer functions, all poles are located at the origin, or as you can see, all of the eigenvalues are located at the origin, which means that any initial condition will go to 0 in finite time. It's exactly 2 steps. So this system is not reachable. Okay, it's not reachable. So technically, so we cannot reach any state other than the origin. Okay, but it is fully controllable. Okay, so from this perspective, you can clearly see that the system can be fully controllable, but it cannot be fully reachable. And keep in mind that the discrepancy between reachability and controllability happens only if you have an eigenvalue at the origin. 1 or 2, doesn't matter. Okay, so if you don't have any eigenvalue at the origin, you can be stable or unstable, it doesn't matter. Reachability and controllability are technically equal concepts. But if you have an eigenvalue that is at the origin, then you need to be careful and you need to dig deeper. Okay, from this perspective, we can say that, okay, if x of d is an element of R, okay, so let's say let's clean that, which means that if x of d is a reachable state, then we know that x of d is also a controllable state. Okay, but if x of d is a controllable state, we may not directly say that it is a reachable state, right? No, exactly, reachable state. From this perspective, you can clearly see that this reachable subspace, we know that it's a subspace of Rn, is also subspace of C, which is a subspace of Rn. So set of all reachable states is a subset of set of all controllable states. Set of all controllable states is a technically a subspace of the whole state space. So if technically R is equal to Rn, automatically we know that C is equal to Rn. So these are important specifically from the perspective of true-false question. And in my opinion, it's good to understand these concepts for understanding better about the state space approach in control systems. That's great. Okay. Do we have anything? Okay, test of reachability for discrete time systems, which is important. Okay. So I have some proofs in the lecture notes. I want you to read it and understand it. I will not ask proofs in the midterm, in the final exam, but I will ask true false questions that are related with these proofs. Okay, so be careful with that. So It won't be directly included in the main questions, but I will definitely ask some questions that are related with the proofs in the true false part. Okay, so how we can test reachability? We have a matrix M, which looks like this. Okay, H, that's great. GH, okay, so it looks very similar, right? G to the power M minus 1 H. This is called reachability matrix. And it exactly looks like the control or reachability matrix for continuous system, and it is. It's one of the beautiful things about state space systems. As you can see, we use the same matrix for, of course, G and H matrices are different if we describe the system, but technically we use exactly the same form to test the reachability for discrete time systems. So when this system is reachable, very simple. We look at the rank M. If it is equal to n, and we know that x is equal to Rn, then it is fully reachable. Or similarly, if range of M is equal to n, range is a subspace, is equal to Rm, and I really recommend you to look at these concepts, that it is a fully reachable system. And we know that if a system is fully reachable, it's also fully controllable. But it's possible that rank of M can be less than n, so it's not fully reachable, but it may be fully controllable, and it will be associated with the zero eigenvalue at equal to 0. And now at that time, you should looking at the eigenvector of the system.